Thanks for joining me in this video. My name is Preston Palmer with Student Engineering. In this video, we're going over an example problem of how to use force equilibrium equations. And if you want more of an explanation on how to use those equilibrium equations, I'll leave a link to my other video down in the description below. So if you find this video helpful, don't forget to subscribe. So in this problem, what we have is a chandelier hanging from 3 wires that weighs 80 pounds. And we're given some of the geometry from this point on the wires where they all connect is 2.4 feet up to the ceiling where they're connected. And in a circle going around, they are 90 degrees from each other on these 2 wires, and then 135 degrees from this other wire. And they are 1 foot out from the center of that circle. So what we need to find is the tension in each one of those wires, given that this chandelier weighs 80 pounds. So the first thing we need to do is we need to draw a free body diagram of this situation to better help us understand the forces that are involved. And so we'll keep this coordinate system of the X, Y, and Z axis, where the origin is where these 3 wires meet. And we're going to represent each of these 3 wires by 3 forces that are labeled as the tension in each of those wires. And then we'll have the force coming down of the gravity pulling down on the chandelier. And so we'll have our X, Y, and Z axis, and our 3 wires coming up as forces. And we will label each wire according to what point it goes from and to. So we'll call this one tension in AB. And then we'll call this one tension in AC. And tension in AD. And then our force coming down from the weight of the chandelier is 80 pounds. And this is our free body diagram. So now what we need to do is we need to better understand the geometry of these triangles formed by these wires so that we can split the forces up into their components of X, Y, and Z so that we can solve our equilibrium equations. So we can see here that these 3 triangles are going to be all the exact same because they're all 1 foot away from the center point, which is on the Z axis, and they're all the same length, 2.4 feet. And so they're all going to form the same angle here and have the same length in each cable. So the first thing we're going to do is we're going to find the length in each cable, and we can do that by using the Pythagorean theorem, because we're given this side of the triangle, which is 2.4 feet, and this side of the triangle, which is 1 foot. So we can write that as the length of the cable, we'll call that L, equals the square root of 1 squared plus 2.4 squared, and you get that that equals 2.6 feet. So each one of these wires is 2.6 feet, a little over 2.5 feet. And now we want to find the angle created between the Z axis and the wire, and we'll call that angle theta. Now we can either use sine or cosine. In this case, I'm going to use cosine, but cosine of theta equals 2.4 divided by 2.6. And so we'll take the arc cosine of both sides and we'll get that theta equals the arc cosine of 2.4 divided by 2.6. And so theta equals 22.6 degrees. And so we'll label that here that this angle is 22.6 degrees. Alright guys, now that we know the geometry of our triangles, we can set up our equilibrium equations for the x, y, and z axis. And we're going to start with the z axis. So, the sum of the forces in the z direction equals 0 because we know our chandelier is not moving, so it's in equilibrium. And then we have each of these forces having a component in the z direction, and we also have our chandelier pulling down only in the z direction. So let's start with the first cable, AB. Well, we want to know its component in z direction. We have this triangle solved here. So if we do the cosine of 22.6, that equals the adjacent side divided by hypotenuse. And so the adjacent side is going to be our z component, and our hypotenuse is going to be the tension in that wire. So we'll multiply the tension over to the cosine, so it'll be the tension of AB times by the cosine of 22.6 equals the z component. Alright, so I had to write it down here because we were running out of space. But we can see, since each of these wires form the same triangle, we're going to get the same z component in each one of these triangles. So we'll have this plus the tension in AC, cosine of 22.6, plus the tension in AD, times by the cosine of 22.6. And then we have our force in the negative z direction, where gravity is pulling down with 80 pounds of force. So we're going to do minus 80. Okay, since this is set equal to 0, we can add the 80 over. And then since each of these are multiplied by the cosine of 22.6, we can factor that out. And we'll have the equation that 80 equals the cosine of 22.6 times by each of these added up. So TAB plus TAC plus TAD. And we can divide cosine of 22.6 over to this side, and we'll end up getting that it is 86.65 equals TAB plus TAC plus TAD. Alright guys, so there we have one equilibrium equation, and we have 3 unknowns in that equation. So we know that we're going to need 2 more equations to be able to solve this system of equations to find these unknown forces. So we're going to set this equation aside right here, and now we're going to do the sum of the forces in the y direction. So the sum of the forces in the y direction equals 0 because it's not moving. And so our wire here from A to C isn't at all in the y direction, so we can ignore it because it's not pulling at all in the y direction. But we have our cable here from A to D that is only pulling in the y and z direction, so it is pulling in the negative y direction, and we can say that the sine of 22.6 equals the y component divided by the hypotenuse, or the tension in the cable AD. You multiply the tension over, and it's tension in AD times by the sine of 22.6 degrees, and that equals the y component of that force. Now remember that it's in the negative y direction, so we'll write it negative TAD sine of 22.6 degrees. Okay, so now we have our force in the tension of wire AB. And this one's going to be a little bit more tricky because it is going not only in the y direction but also in the x direction, and we need to solve the component of the y force. So what we can see here is if we take the sine of 22.6 times by the tension in this wire, kind of like we did here, we'll get the component that's going in this direction of this wire. So if we do that, we'll have the force in this direction. And you'll notice how this makes a little triangle here, where we know since this is 135 degrees, it will be coming exactly at 45 in this angle. So these two sides are going to be the same. Or in other words, the x and y components of this force are going to be the same. And if we take the cosine of 45 degrees times by this component right here that we'll call F for now, we'll call this component force F. If we take the cosine of 45 degrees times by the force F, we will get the y component of that force in the cable. So kind of going over that again, we'll have plus the force F is going to equal the component of this cable going in this diagonal direction, and that's going to be that the sine of 22.6 degrees equals F divided by the tension in cable AB. So we'll multiply that over, and we'll get that the force F is equal to TAB times the sine of 22.6. But that's just that F component. It's not the force in the y direction. It's exactly between the x and y direction. So we need to find the y component of F. And we can see that the sine, or the cosine of 45 degrees is equal to our y component of that force divided by F, which is the hypotenuse of that triangle. And so if we multiply F over to this side, we can get the component in the y direction equals this, which is F, times by the cosine of 45 degrees. So we'll write that up here. Times the sine 22.6 times by the cosine of 45 degrees. Get this out of the way. Alright guys, so that was a little complicated. If you need to watch that part again, go ahead and do so. It just takes a little bit to figure out and wrap your mind around the geometry and what's kind of happening there, but I promise it makes sense and it works out. So what we're going to do, we're going to add this term over to the other side, and then we'll get that TAD sine of 22.6 equals TAB sine of 22.6, and then the cosine we're going to rewrite. Cosine of 45 degrees is square root of 2 over 2, and so we'll just replace that as a simpler form. And you'll notice on both sides it's being multiplied by sine of 22.6, so we can cancel that out, and we end up getting that TAD is equal to the square root of 2 over 2 times by the tension in the wire AB. Alright guys, so there we have another equation that we can use in our system of equations to solve for unknowns. And you'll notice that it only has two of the variables, but that's going to be okay, it's going to work out in the end. So we're going to set this aside right here, and we're going to set up our third equilibrium equations. So the sum of the forces in the x direction equals 0, and that equals So we have our cable that's only going in the x direction, and that's cable AC. And we have our other cable that's going in both the x and y directions, and that's going to be very similar to what we did before. So this one is going to be the sine of 22.6 times by the tension in the angle is the x component. So TAC sine of 22.6, and remember that's in the positive direction. This one is going in the negative x direction, so we're going to do minus. Now guys, if you're kind of confused on how I got that with the geometry of that, I've done it earlier in this video, but if you need me to go slower, let me know down in the comments below, and I'll fix that for future videos. But we're going to minus the x component in this side because it's going in the negative x direction, and it's going to be the same because we're going to still have F, and you remember that was the tension in AB times by the sine of 22.6. And then we multiply that by, last time we multiplied it by the cosine of 45 degrees, but this time we want this side, which is the opposite, so we're going to use sine of 45 degrees times by F, and that'll give us the x component of this. So remember that F was TAB sine of 45, not 45, sine of 22.6 times by the sine of 45. Alright, so we're going to add this over, and again we're going to notice that there's sine of 22.6 on both sides, and again the sine of 45 degrees is also square root of 2 over 2. So we're going to end up that TAC equals square root of 2 over 2 TAB. And so we notice that that's almost the exact same equation that we got in the last one, and that's because both of these forces are either only in the x direction or the y direction, and so that's going to mean they have the same force. But we're going to notice in the end that the force in this cable is not going to be the same as the other two. And so now that we have three equations, we can solve for those unknowns, and we can see that this equation and this equation are solved for TAC and TAD, and we can replace those in here in this equation, and we'll have one equation just with the variable TAB. So 86.65 equals TAB plus the square root of 2 over 2 TAB and then again the other one's the same, right? So plus the square root of 2 over 2 TAB. So we can combine those, and it dividing by 2 is going to go away, so we're going to get the square root of 2 TAB from those, and this will be 1. We're going to factor out the TAB in that, and we're going to get 86.65 equals 1 plus the square root of 2 times by TAB. Because we factored out the TAB, there's a 1 in front of this, so it's going to be 1 plus the square root of 2. We'll divide this over to 86.65, and then we'll get that 35.9 equals TAB. So there we have the force in one of those cables, and we can plug them back in to our other two equations. Remember, the other one looks like this for TAC, and then we're going to get, since they're equal, we'll get that the square root of 2 over 2 times by 35.9 equals TAC, and it also equals TAD, because they're the same equation.
So we'll multiply those together and we'll get that TAC and TAD equals 25.4. And remember, we need to label these. This will be in pounds because we're dealing with force in pounds. And so our final answer is that TAB equals 35.9 pounds, TAC equals 25.4 pounds, and TAD also equals 25.4 pounds. Alright guys, that's it. I hope you found that helpful, and if you didn't understand anything, please let me know down in the comments below. But if you found this video helpful, please hit that like button, and don't forget to subscribe.